At this exact second, somewhere in the deep darkness of space, a massive cloud of ordinary dust and gas that has been drifting in absolute silence for billions of years is beginning to collapse under its own weight. It packs together so violently, so relentlessly, that the center becomes unimaginably hot. The particles of gas are literally crushed into one another, fusing together, and a powerful engine of light ignites. A star is born. It will shine for an incredibly long time. Throughout its life, it will act as a cosmic forge, building the heavy elements inside its body that serve as the building blocks for future worlds: carbon, oxygen, and iron. And when its time finally comes to an end, it will either fade away quietly or tear itself apart in a massive explosion, scattering those elements across vast distances. That ash will mix with other cosmic dust, collapse again, and new stars will form from the wreckage of the old ones. This cycle has been happening since the dawn of time. The fire has been burning for nearly 14 billion years, and it will keep burning for a while longer. But here is the thing that most people don't think about, the thing that changes how you look at the night sky once you truly understand it. We are not in the beginning of this story. We are not even in the middle. We are near the end. The universe is 13.8 billion years old. That is a number so large that it becomes meaningless the moment you try to feel it. So let's try a different way. Imagine the entire history of the cosmos compressed into a single year, one calendar year, from January 1st to December 31st, with the Big Bang happening at the very first second of January 1st. On that scale, the first stars don't appear until January 22nd. Our galaxy, the Milky Way, begins to take shape around March. The sun, our sun, isn't born until early September. Earth forms a few days later. The first complex life on Earth doesn't appear until November. Dinosaurs rise and fall in the last week of December. All of human civilization, every empire, every war, every invention, every song ever written, happens in the final 17 seconds before midnight on December 31st. And thus, right now, this moment, you listening to this, we are at 1 second to midnight. That's where we are in the story of stars. Now here is what most people don't realize about that story. For most of human history, we looked at the night sky and saw permanence. The stars were fixed, eternal. They were the one thing that didn't change. Civilizations rose and fell. Rivers changed course. Mountains eroded. But the stars were always there. The ancient Greeks called the cosmos cosmos precisely because it meant order, stability, the eternal backdrop behind all the chaos of human life. We now know that is completely wrong. The stars are not a backdrop. They are not permanent. They are not even particularly old. Most of them, relative to what the universe is capable of, they are, in the grand view, a temporary phenomenon, a phase the universe is going through, and that phase is already winding down. We are living inside a dying fire, and the fire is beautiful, and has been burning for a very long time, and it will keep burning for an almost incomprehensible time longer, but it is, without any ambiguity, going out. That is what this film is about, not with alarm, not with grief, exactly, but with the full weight of what it means to exist in the middle of something that will not last forever. Let's start at the very beginning, because to understand where we're going, you need to understand what stars actually are and where they come from. When the universe was born, in whatever event or process we call the Big Bang, it produced matter, mostly hydrogen, some helium, trace amounts of lithium. That was it. No carbon, no oxygen, no iron, no silicon, nothing complex. Just the two simplest atoms, spread unevenly through an expanding void. The unevenness is important. If the early universe had been perfectly smooth, if every region of space had exactly the same density of matter, then gravity would have had nothing to work with. Everything would have expanded outward uniformly, forever. And the universe would today be an extremely thin, extremely cold, extremely boring gas. But it wasn't perfectly smooth. There were tiny fluctuations, regions that were very slightly denser than average, and regions that were very slightly less dense. And gravity patient and relentless, began to work on those fluctuations. The denser regions attracted more matter. The less dense regions gave up what they had. Over hundreds of millions of years, the denser regions grew into clouds. The clouds grew denser still. And eventually, in some of those clouds, the density became high enough and the temperature became high enough that hydrogen atoms at the center began to fuse. The universe had its first light. Those first stars were nothing like our sun. They were enormous, hundreds of times more massive in many cases. They burned with ferocity we have no parallel for, and they were composed entirely of hydrogen and helium, because nothing heavier existed yet. Astronomers call them population 3 stars, and we have never directly observed one, not a single confirmed detection. They were born so early and they burned so fast, lasting only a few million years before exploding, that their light has been stretched and diluted by the expansion of the universe until it falls below what our current instruments can detect. We know they existed because the universe we see today requires them. The heavy elements in your body, the carbon in your cells, the calcium in your bones, the iron in your blood, none of that existed in the early universe. It had to be made somewhere. And stars are the only place in nature where hydrogen and helium can be fused into heavier elements. The first stars created those elements, then died in supernovae that scattered them through the cosmos, seeding the next generation of gas clouds with ingredients for something more complex. You are, in the most literal sense possible, the ash of ancient stars. That phrase is often said for effect and then forgotten, but sit with it for a moment. The atoms in your hand right now were billions of years ago inside a star that no longer exists, a star whose death made your existence possible. There is nothing metaphorical about that. It is chemistry and physics. It is the actual history of the matter you are made of. After those first enormous stars died, the universe went through a transformation. The gas was enriched. The heavy elements changed how clouds cooled, which changed what kind of stars could form, which changed what those stars did when they died. Gradually, over hundreds of millions of years, star formation became something more like what we see today. Smaller stars became possible, longer-lived stars, stars that could burn for billions of years instead of millions. Planetary systems formed around them. Stable environments persisted for long enough that chemistry could become biology. The universe was learning, in a sense, not consciously. Nothing about this is conscious. But the physical and chemical conditions for complexity were slowly being built, one stellar generation at a time. And then, roughly 10 billion years ago, something remarkable happened. The universe reached its peak. Astronomers have a name for it: cosmic noon. It refers to the period approximately 10 years ago when the universe was forming stars at the highest rate it has ever achieved or ever will achieve. About 3 billion years after the Big Bang, the star formation rate reached its peak and has been declining ever since. Think about what that means. The universe, in its youth, was a furnace. Galaxies were colliding constantly, driving enormous shock waves through gas clouds, compressing them, triggering the collapse of millions of stars at once. The raw material, cold hydrogen and helium, the fuel for star formation, was abundant everywhere. It hadn't been used up yet. It hadn't been expelled from galaxies by the energy of supernovae. It was just there, waiting, and gravity was converting it into stars as fast as physics would allow. If you could have stood outside the universe at that moment and looked at it, which is of course impossible, but try to imagine it, you would have seen something almost violent in its brightness. Galaxies blazing, quasars igniting at the centers of the largest structures, pouring out more energy than entire galaxies do today. The rate of stellar birth was staggering by any measure we can apply. We know this not from speculation, but from observation. Data from Hubble, JWST, Fermi, Euclid, and more all show a star formation history that peaked around 10 to 11 billion years ago and has declined ever since. When we look at distant galaxies, and looking at distant galaxies is looking into the past, because light takes time to travel, we see galaxies that are forming stars at rates that dwarf anything happening in the modern universe. The further away the galaxy, the further back in time we're seeing, and the more active the star formation. The picture is consistent across dozens of independent measurements from different instruments, different wavelengths, different research teams on different continents. The star formation rate density peaked approximately 3.5 billion years after the Big Bang and declined exponentially at later times, with an e-folding timescale of 3.9 billion years. This is not a contested finding. This is one of the most robustly established facts in modern cosmology. Now, let's make that real with some numbers. The rate of star formation in the universe today is only 1/30th of what it was at its peak. Some more recent measurements put the figure even lower. Today, the star formation rate is only around 3% of what was back at its maximum, and it continues to drop. 1 in 30, 3%. Imagine a city that at its height was building 30 new houses every day. Now it builds one, and that one per day is still declining. That's roughly where we are in the cosmic story of star formation. Half of all the stellar mass we observe today was formed before a redshift of 1.3, meaning more than half of all the stars that will ever exist in the observable universe had already been born more than 7 billion years ago. Our sun itself was a latecomer. It formed about 4.6 billion years ago, which was already well into the declining phase of cosmic star formation. By the time our sun lit up, the universe had already passed its creative peak by several billion years. We are the children of a universe past its prime. What caused the peak? And what caused the decline? Both questions have answers, not perfectly complete answers, but well-supported ones. The rise to cosmic noon was driven primarily by the structure of the early universe. In the beginning, matter was densely packed relative to today. The expansion of space hadn't yet stretched everything apart. Gas was cold and abundant. Galaxy collisions were frequent, and collisions between galaxies are extraordinarily efficient at triggering star formation. When two galaxies interact, the shock waves they generate compressed gas clouds at enormous scales, creating what astronomers call starbursts, brief, intense episodes of star formation that can produce more new stars in a few tens of millions of years than a quiet galaxy would in a billion. So the early universe was loud, violent, productive. The decline after cosmic noon is driven by several factors working together. First, the raw material runs out. Every star that forms takes hydrogen out of circulation. Some of that hydrogen is returned to the interstellar medium when the star dies, enriched with heavier elements. But not all of it. Some hydrogen ends up locked in stellar remnants, white dwarfs, neutron stars, where it can no longer participate in forming new stars. The total reservoir of star-forming gas has been shrinking since the beginning. Second, the universe keeps expanding, and that expansion has been accelerating for the last several billion years, driven by what we call dark energy. The cosmological constant suppresses cosmic structure formation, meaning that as dark energy increasingly dominates the dynamics of the universe, it becomes harder and harder for matter to collapse into dense structures that give birth to stars. The gravitational gathering of gas into galaxies, and of gas within galaxies into star-forming clouds, requires matter to overcome the expansion of space. As the expansion accelerates, that becomes progressively more difficult. Third, the galaxies themselves are aging. The largest, most massive galaxies, the giant ellipticals at the centers of galaxy clusters, went through their period of intense star formation early and have been largely dead for billions of years. They exhausted their gas supply during cosmic noon and have been coasting on their existing stellar populations ever since. What remains active today are primarily smaller, less spectacular systems. Astronomers using data from ESA's Euclid and Herschel space telescopes confirmed as recently as late 2025 that star formation has already peaked in the cosmos, and that the universe is bound to get steadily colder and deader from here on. By studying the heat emitted by stardust in more than 2 million galaxies, the team found that galaxies have grown slightly cooler and seen star formation rates slow down over the past 10 billion years of cosmic history. 2 million galaxies. The sample is not small. The trend is not ambiguous. One of the researchers involved described it with unusual directness for a scientific paper. The universe, they said, will just get colder and deader from now on. Not a hypothesis. An observed trend confirmed by the largest photometric survey of galaxy dust emission ever conducted. We are living inside that trend. It is worth pausing here to ask a question that most people never ask, because the answer is slightly disorienting. What does it feel like to live in a universe past its peak? The honest answer is, it doesn't feel like anything in particular, because the timescales are so vast that no human life, no human civilization, no species has ever existed or likely ever will exist on Earth could possibly perceive the decline directly. From one generation to the next, the sky looks the same. The stars seem eternal. The Milky Way arches overhead on a dark night, as it has for every human who has ever lived, and it will continue to do so for every human who ever will live. The decline is happening, but it is happening in slow motion, so extreme, that it makes geological change look rapid. The star formation rate today versus what was a million years ago is effectively identical. A million years ago, in cosmic terms, is barely an eye blink. The curve has the shape of an exponential decay. It fell fast after the peak, then flattened into a long, slow, gentle descent that will continue for billions of years. So we are not living in a universe that is visibly dying. We are living in a universe that is, in a very real sense, in its long afternoon. The morning was brighter, more turbulent, more generative. The night is coming. Not soon, not in any time scale that should disturb anyone's sleep, but coming. And the stars we see tonight are, many of them, the last generation. Let's be precise about what last generation means, because it's easy to misunderstand. Some of the stars currently burning in the sky will outlive the universe's ability to make new ones. The sun is probably not among them. It has about 5 billion years left, and star formation will continue for much longer than that. But among the stars visible to you on a clear night, there are red dwarfs, dim, cool, slow-burning stars that will still be shining long after the last new star is born anywhere in the observable universe. The faint star next to the bright one, the one your eye passes over, that might be the last kind of star the universe ever makes. There's another thing about cosmic noon worth dwelling on, something that sits at the intersection of science and something harder to name. The comoving rates of star formation and central black hole accretion follow a similar rise and fall, offering evidence for coevolution of black holes and their host galaxies. The supermassive black holes at the centers of galaxies grew most rapidly during the same era when star formation peaked. The two processes are connected. The same gas inflows that fed star formation also fed the black holes. When one declined, so did the other. The universe's most productive era was also its most violent, stars being born in their millions, black holes devouring gas at rates that made entire galaxies glow brighter than anything in the modern cosmos. Creation and destruction at maximum scale simultaneously. What we have now is quieter, steadier. The universe has settled into something more sedate. Some cosmologists describe it, somewhat poetically, as the universe running out of ideas. The grand machinery of structure formation is still running, but at a fraction of its former pace. The galaxies that exist now are largely the galaxies that will always exist. The stars being born today are, by and large, the last cohort. About 25% of all stellar mass formed before the peak of cosmic star formation, and another 25% formed after redshift 0.7, meaning after about 6 billion years ago. So the bulk of star formation in the history of the universe was concentrated in a relatively narrow window, a few billion years on either side of cosmic noon. We live in the long tail of that distribution. Statistically speaking, most stars that will ever exist already do exist. Now, 13.8 billion years after the Big Bang, new stars are uncommon, not rare. New stars are still being born, including in our own galaxy, but uncommon relative to what was possible, relative to what was happening 10 billion years ago. The fires are banking. The question is not whether they will go out. They will. The question is what happens in the long, slow interval between now and then. And that is where we go next. Because between the universe we see tonight and the final darkness, there's a chapter of cosmic history that stretches for a duration so vast it makes everything that has come before look like an introduction. The last stars are not dying soon. They are dying over a period of trillions of years. And the last of them, the dimmest, the coolest, the ones you can't even see with the naked eye, will outlast everything else the universe has ever made. There is a particular kind of silence that comes after something great has ended, not the silence before. That is anticipation, potential, the hell breath before beginning. This is the other kind, the silence of aftermath. The quiet that settles over a hall after the last musician has packed up and left, when the chairs are still warm and the acoustic memory of performance still lingers faintly in the walls, but the sound itself is gone. The universe has been in that kind of silence for about 7 billion years. It doesn't look like silence from where we stand. The night sky is full of light. The Milky Way contains hundreds of billions of stars. Galaxies are still forming new ones. The machinery is clearly still running. But if you could see the whole picture, if you could stand outside space and time and watch the rate of stellar birth across the entire observable universe as a single curve plotted against cosmic time, what you would see is unmistakable. The peak was long ago. What we are living through now is the exhale. Let's talk about what's actually happening in the universe right now, at the level of gas and gravity and physics, to understand why the decline is not some temporary dip, but a permanent, irreversible trajectory. Star formation requires 3 things: cold gas, enough of it concentrated in one place, and sufficient time for gravity to pull it together. All 3 of those conditions are becoming harder to meet. The gas is the most fundamental issue. The universe has a finite amount of hydrogen and helium, the primordial fuel. It was all made in the first few minutes after the Big Bang, and no significant new supply has been created since. What exists is what exists. And over 14 billion years of continuous star formation, that supply has been steadily consumed. It isn't used up all at once. When a star dies, much of its mass is returned to the surrounding medium. A star like our sun will eventually shed its outer layers in a process called a planetary nebula, a beautiful, expanding shell of gas enriched with carbon and oxygen, and that material re-enters a galactic ecosystem, available in principle for the next generation. Massive stars die more violently, in supernovae, but the principle is the same. Much of the gas is recycled, but not all of it. Every stellar generation locks some fraction of matter away in remnants, white dwarfs, neutron stars, where it sits inert for timescales that make the current age of the universe look brief. And some gas is heated so violently by supernovae and by the energy released by accreting black holes that is expelled entirely from a galaxy, launched into the intergalactic medium where it becomes too diffuse, too hot, and too scattered to ever collapse into stars again. Each cycle is slightly less efficient than the last. The universe is a machine that runs on a fuel supply. It is slowly depleting and cannot replenish. Then there is the question of structure. Stars don't form in empty space. They form in molecular clouds, dense, cold regions of the interstellar medium that have been compressed to the point where hydrogen molecules can form and where the gas can cool efficiently enough to collapse. The formation of those clouds depends on the large-scale structure of galaxies, the density waves that create spiral arms, the turbulence of the interstellar medium, the pressure balance between hot and cold gas. In the early universe, galaxies were building that structure from scratch. Gas was streaming in along cosmic filaments, the vast web of dark matter that spans the universe. And that inflow was continuously replenishing the star-forming reservoirs inside galaxies. New gas arriving from outside the galaxy was crucial. It was essentially the fuel delivery system. That inflow has been declining for billions of years, for the same reason that everything on large scales is slowing down. The expansion of the universe, driven by dark energy, is progressively stretching the filaments thinner, reducing the density contrast between them and the surrounding voids, and making it harder for gas to flow along them into galaxies. The cosmic web is still there. It will always be there in some form, but its ability to channel gas into galaxies, to refuel the engines of star formation, has been weakening steadily and will continue to weaken. There is no mechanism on the horizon that reverses this. No cosmic event that is expected to restart the inflow in any meaningful way. The gas supply is running low. The delivery system is failing. And what gas remains inside galaxies is being consumed, ejected, or locked away with every passing billion years. There is one more factor worth understanding. Because it is perhaps the strangest, the universe is working against itself. When stars form in large numbers, they don't just sit there and burn quietly. The most massive among them pour out ultraviolet radiation so intense that it can ionize and heat the surrounding gas, precisely the gas that would otherwise be available for forming more stars. When massive stars die as supernovae, the shock waves they generate can compress nearby clouds and trigger new star formation, but they can also shred clouds apart entirely, dispersing gas that was on the verge of collapsing. And at the centers of galaxies, supermassive black holes, when they are actively accreting when they are on, release energy that can heat the entire gaseous halo of the galaxy, suppressing the inflow of cold gas for hundreds of millions of years at a time. This is called feedback. It is one of the central concepts in modern galaxy formation theory. Stars and black holes don't just passively consume gas. They actively regulate how much gas is available for future star formation. And as galaxies age, the feedback processes increasingly favor suppression over stimulation. The most massive galaxies essentially switched themselves off billions of years ago in a process astronomers call quenching. They produce so many stars so fast that they heated and expel their own gas supply. And they've been red, passive, and largely starless ever since. What remains active, what is still forming stars in the modern universe, is primarily the less massive galaxies, the dwarf systems, and the outskirts of larger galaxies with feedback from central black holes is weaker. The universe is becoming dominated by the red and the dead. Now, let's talk about what this looks like from inside the Milky Way. Our galaxy is still forming stars. It is one of the active systems. Current estimates suggest the Milky Way forms somewhere between 1 and 3 solar masses worth of stars per year, meaning that each year, our galaxy produces new stars with combined mass roughly equal to 1 to 3 times our Sun. The uncertainty in that number is real. Measuring the current star formation rate of our own galaxy is surprisingly difficult, partly because we're inside it and can't see the whole thing at once, and partly because star formation is a patchy, irregular process that varies across the galaxy's disk. For context, the Milky Way may have formed stars at a rate of tens of solar masses per year during its most active period, several billion years ago. We are well past that. Our galaxy is, in the grand scheme of things, winding down. Not rapidly, not dramatically, but measurably. The Andromeda Galaxy, our nearest large neighbor, currently about 2.5 million light-years away, is on a collision course with the Milky Way. The collision, which is expected to begin in roughly 4 to 5 billion years, will likely trigger a burst of star formation as the two galaxies' gas clouds collide and compress. So in the far future, from the perspective of any hypothetical observers in the merged galaxy, there may be a brief renewal, a flash of stellar birth brighter than anything seen in our galactic neighborhood for billions of years. But it will be brief. After the merger, the combined galaxy will settle into a large elliptical, the type of galaxy that is, almost by definition, largely done forming stars. The gas will have been consumed or expelled during the violent interaction. What comes after the merger is quiet, a brief, brilliant last flourish, and then the long settling into stillness. Step back even further, to the scale of the observable universe. We can observe galaxies out to a distance of about 46 billion light-years. That's the current radius of the observable universe, accounting for the expansion of space. Within that volume, there are hundreds of billions of galaxies. And when we study them, what we find is a population that skews increasingly toward the old, the passive, the red. The blue galaxies, the ones with active star formation, glow with the ultraviolet light of young, hot, massive stars, are becoming less common. The red galaxies, dominated by old stellar populations, their star formation long since quenched, are becoming more numerous as more and more blue galaxies exhaust their gas and transition to the red, dead population. This transition has been happening for at least 10 billion years. It is not a recent development, but its cumulative effect is visible in galaxy surveys, and it points in one direction only. At some point in the future, the exact timing depends on models and assumptions, but the broad picture is consistent across them. The rate of star formation in the observable universe will drop below one new star per year, integrated across all galaxies combined, then below one per decade, then below one per century. And eventually, the number of new stars forming will approach zero, not instantaneously, not even quickly on cosmic timescales, but asymptotically. Inevitably, the curve approaches the baseline. The exhale continues until there is no breath left. There is something philosophically significant about the shape of this curve that I want to sit with for a moment before we move on. The decline of star formation is not a catastrophe. It is not a sudden event, not a breaking point, not a moment where someone could look up and say, that was the day the universe changed. It is a gradual fading, stretched across timescales that no mind can directly experience. The difference in the night sky between the universe as it is now and the universe as it will be in a billion years is effectively undetectable by human senses. And yet the direction is clear, and the destination is certain. This is a different kind of ending than the ones we usually imagine. We tend to think of cosmic endings as dramatic. The big crunch, the heat death, the collision of galaxies, the explosion of stars. And those things exist or will exist. But the ending of the age of star formation is quieter than any of them. It is less an explosion than an exhalation, less a death than a gradual stepping back from the act of creation. The universe is not being destroyed. It is simply becoming less generative. And in the silence that follows that long, slow exhale, there will still be light. There will still be stars. Not many, and not bright by the standards of cosmic noon, but there will be light provided by the last stars. If you went outside tonight, away from any city, away from any artificial light, and looked up on a clear, dark night, you would see somewhere between 2,000 and 5,000 stars with the naked eye, a few thousand points of light scattered across the dome of the sky. Almost none of them are the kind of star that will be the last to shine in the universe. The stars you can see, the ones bright enough to be visible to unaided human vision, are almost entirely the wrong type. They are too bright, which means they are too hot, which means they are burning their fuel too quickly. The brilliant blue-white stars like Rigel and Sirius will be dead in tens or hundreds of millions of years. Stars like our sun will last 10 billion years in total. Impressive by human standards, modest by cosmic ones. Even the cooler orange stars will be gone within a few tens of billions of years. The last stars are almost invisible. They are called red dwarfs, and they are the most numerous type of star in the universe, and almost none of us have ever consciously seen one. Let's understand what a red dwarf actually is, because the physics of their longevity is not an accident. It is a consequence of their nature in a way that is, when you think about it carefully, almost elegant. A red dwarf is a star with a mass somewhere between roughly 8% and about 40 to 50% of the mass of our sun. The lower limit is important. Below about 8% of solar mass, there is enough gravitational pressure to sustain hydrogen fusion at all, and the object becomes a brown dwarf, a failed star, warm but not truly shining. Above the upper limit, the star starts to resemble our sun more than a red dwarf, with a different internal structure and a shorter lifespan. Red dwarfs are small. The smallest of them are barely larger than the planet Jupiter. They are dim. Red dwarfs have luminosities between about 0.0001 and 0.1 times that of the sun. The brightest red dwarf is still 10 times fainter than our sun. The dimmest are 10,000 times fainter. They glow a deep orange-red, far cooler than the yellow-white of our sun, with surface temperatures roughly half that of our star. And they are extraordinarily common. Red dwarf stars are the most common stars in the universe, comprising up to 80% of all stars. In our own galactic neighborhood, The majority of stars within a few dozen light-years of Earth are red dwarfs. Proxima Centauri, the closest star to our Sun, at 4.24 light-years, is a red dwarf. Barnard star, the second closest, is a red dwarf. Of the 20 closest stellar systems to our Sun, the majority contain red dwarfs. They are everywhere. They are the dominant form of stellar life in the universe, and most people have never knowingly looked at one. Now, here's the thing about red dwarfs that changes everything when you think about the long-term future. The lowest mass red dwarfs can last for 10 trillion years, sipping away at their hydrogen fuel with extraordinary patience. 10 trillion years. The universe is currently 13.8 billion years old. 10 trillion years is roughly 700 times the current age of the universe. If the current age of the universe were 1 day, then the lifespan of the smallest red dwarfs would be nearly 2 years. This is not a rounding error or a rough estimate. It follows directly from the physics of how these stars burn their fuel. Nearly 100% of a red dwarf's initial hydrogen is available as fuel over the course of its life, in contrast to an estimated 10% for the Sun. The reason is structural. In stars like our Sun, the core burns hydrogen, but the outer layers don't participate in fusion. The helium ash that builds up in the core eventually disrupts the fusion process, which is why Sun-like stars eventually leave the main sequence, swell into red giants, and die. Only about 10% of the total hydrogen in the star ever gets used. In red dwarfs, the entire star is convective. The material circulates throughout. Hot plasma from the core rises to the surface, and cooler material from the surface descends into the core. This means fresh hydrogen is continuously being supplied to the fusion zone, and helium ash is continuously being carried away from it. The star uses essentially all of its hydrogen, not just the 10% in the core. By some estimates, the lifespan of a red dwarf with 1/10 of the Sun's mass could be 10 trillion years. Truly mind-boggling when we consider the relatively young age of the universe. There is a corollary to this that is almost too strange to fully absorb. Because the universe is only 13.8 billion years old, not a single red dwarf has died yet. Every red dwarf that has ever formed is still burning. Every single one of the trillions that exist is still in the early stages of its life. We have never seen a red dwarf die, not once in the history of human astronomy or in the history of the universe. There are no red dwarf remnants, no white dwarfs that were formerly red dwarfs, because none of them have had time to complete that journey. The universe is not old enough. Every red dwarf you could observe, if you could observe them, and they're mostly too dim to see without instruments, is, in the context of its own lifespan, an infant. The most ancient red dwarfs, born in the first few billion years after the Big Bang, are perhaps 1% through their lives. The youngest ones formed recently are even less than that. They are just beginning. Red dwarfs will outlive all other stars in the universe. They will be the last stars to ever shine, and their light will be the final light before the eternal darkness. This deserves to be stated plainly, without embellishment, because the fact itself is more striking than any embellishment could make it. At some point in the future, in the range of 100 trillion years from now, according to a framework proposed by astrophysicists Fred Adams and Gregory Laughlin, the last new star will be born. The last cloud of gas will collapse under gravity for the last time and ignite hydrogen fusion. And after that, no new stars will ever form again. We are living in what astrophysicists Fred Adams and Gregory Laughlin dubbed the Stelliferous Era, the age of stars, which stretches from when the universe was 1 million years old to when the universe will be roughly 100 trillion years old. 100 trillion years is the rough upper boundary. After that point, the gas supply will be exhausted or so dispersed and so heated that no further collapse into stars is expected. The machinery stops. But the stars that form before that boundary don't all die immediately. The red dwarfs, in particular, keep burning for an almost incomprehensible time afterward. The last generation of stars will exhaust any remaining hydrogen fuel available for consumption, and then the universe will be populated only by degenerate stellar remnants. Black holes, white dwarfs, brown dwarfs, and neutron stars. The transition is not abrupt. It is drawn out over trillions of years. First, the most massive stars die, then the intermediate ones, then the sun-like stars, then the lower mass stars, each on their own schedule, each fading out quietly or violently according to their nature. And then, long after all of those are gone, the red dwarfs are still there, burning slowly, burning patiently, in a universe that has largely gone dark around them. Imagine that future sky, not the sky of tonight, dense with points of light, the Milky Way a river of stars overhead, the sky of 100 billion years from now, from whatever vantage point might exist. The massive stars are long dead. The medium-mass stars are long dead. The sun-like stars, the yellow and orange dwarfs, have, most of them, swelled into red giants, consumed their planetary systems, shed their outer layers, and collapsed into white dwarfs, slowly cooling in the dark. What remains of the red dwarfs? Dim, orange-red points, separated by enormous distances as a continuing expansion of the universe pushes galaxies further apart. Most of them will, by that point, have been flung out of their host galaxies entirely, or stranded as their galaxies merge into the vast, diffuse elliptical systems that will dominate the late universe. The sky will be darker, much darker, not black, not yet, but emptier, fewer stars by orders of magnitude. The ones remaining are dim, invisible to any human eye that might hypothetically look up, glowing only in the infrared, radiating heat rather than visible light in any significant quantity. They are not brilliant. They are not dramatic. They are persistent. And they are running on a clock that won't reach zero for a very, very long time. There is an unexpected dimension to the story of red dwarfs that science has only begun to fully appreciate in recent decades, and it has to do with life. Not our life. Not life as it currently exists on Earth, but the question of whether life, in principle, has more future ahead of it in the universe than behind it. Life as we know it first became possible about 30 million years after the Big Bang, when the first stars seeded the cosmos with the necessary elements like carbon and oxygen. Life will end approximately 10 trillion years from now, when the last stars fade away and die. Within that window, Avi Loeb of the Harvard-Smithsonian Center for Astrophysics and his colleagues found that the chance of life grows much higher in the distant future. In fact, chances of life are 1,000 times higher in the distant future than now. This is a striking claim, and it's worth being precise about what it means and what it doesn't mean. It is not a claim that life definitely exists elsewhere, or that it will definitely arise around red dwarfs in the far future. It is a probabilistic argument based on the lifetimes of stars. The longer a star lives, the more time any planet orbiting has to develop life. Red dwarfs live so much longer than sun-like stars that even if the probability of life arising per unit time around a red dwarf is lower than around a sun-like star, the cumulative probability over trillions of years can exceed the cumulative probability over a few billion years. The dominant factor, as Loeb's analysis found, is the lifetimes of stars. The smallest stars weigh less than 10% as much as the sun. They will glow for 10 trillion years, giving life ample time to emerge on any planets they host. As a result, the probability of life grows over time. If this analysis is correct, and it represents one perspective in an ongoing scientific discussion, not a settled consensus, then we, as life that exists now, are early. We are cosmically premature. The universe has barely begun its biological story, if it has one at all. There are real complications. Red dwarfs are not uniformly gentle hosts. Many of them are highly active in their youth, emitting intense flares of ultraviolet and X-ray radiation that could sterilize any nearby planet. Planets in the habitable zone of a red dwarf must orbit very close to the star, close enough that tidal forces may lock them, so that one hemisphere always faces a star and the other always faces away, creating extreme temperature contrasts that complicate the prospect for surface life. These are genuine challenges, and they are not resolved. The scientific community is actively debating whether red dwarfs are good or bad hosts for life. Some recent modeling suggests that certain configurations, planets with thick atmospheres or large oceans that can redistribute heat might be viable. Others suggest the flaring and tidal locking are deal breakers for complex life. What is not in dispute is the timescale. Whatever the answer about habitability, red dwarfs represent the last window in cosmic history where stellar energy is available to drive chemistry, to warm surfaces, to provide the kind of sustained, stable energy input that life as we understand it requires. After the red dwarfs go, that window closes forever. Let's come back to that number. 100 trillion years for the end of the Stelliferous Era. 100 trillion years is the rough timescale for the last star to form. But the last red dwarfs won't die until trillions of years after that. The end of the era of star formation and the end of the era of starlight are not the same moment. There's a gap, an enormous gap, between the last birth and the last death. During that gap, the universe will contain stars, living, burning, shining stars, but no new ones will be forming. The population of stars will be slowly declining, one by one, each burning out on its own schedule. The most massive of the remaining ones first, the least massive last. It will be a universe in which every star is an orphan of a dead age. Every star still burning will be a survivor from an era of creation that has ended. The sky will be getting darker, year by trillion year, star by star. And the last one standing will be the dimmest, the smallest, the ones that have been burning unnoticed, at the periphery of our attention for the entire history of human astronomy. The final inheritors of the Age of Fire. They will burn alone in an expanding, darkening, cooling universe for timescales that make everything we've described so far. The 14 billion years of cosmic history, the 10 billion years of stellar decline, the entire story of Earth and life and humanity look like a prologue. And then, at last, they too will go out. Here is something worth sitting with before we go further. The last red dwarf star, the dimmest, coolest, most patient star the universe will ever produce, will not die in any dramatic fashion. It will not explode. It will not collapse into something violent. It will simply cool, gradually. Across timescales that dwarf everything that came before, it will lose heat into surrounding void until it can no longer sustain fusion. And then it will go dark. No explosion. No announcement. Just the end of light. When that happens, somewhere around 10 trillion years from now, give or take the kind of uncertainty that makes a billion years of error feel like a rounded mistake, the Stelliferous Era ends. The age of stars is over. Every star that will ever burn has already burned. The universe crosses a threshold from which there is no return, and what comes next has a name, the degenerate era. The word degenerate here is not moral commentary. It is physics. It describes a specific state of matter that has been compressed to the point where quantum mechanics, rather than thermal pressure, is the force holding it together. Electrons pack so tightly that they resist further compression not because of heat, but because of the Pauli exclusion principle, a rule of quantum mechanics that says no two electrons can occupy the same quantum state simultaneously. This pressure, cold, quantum, in different temperature, is what keeps a white dwarf from collapsing. It is a thing that endures long after the fire goes out, and the degenerate era is populated by exactly these objects. Let's be precise about what the universe looks like after the last star dies. The most massive stars, the ones that burn brightest and fastest, are already gone by this point, long gone, dead billions or trillions of years earlier. They ended as neutron stars, objects roughly 20 kilometers across, containing more mass than our sun, composed almost entirely of neutrons packed to densities that would compress the entire mass of Earth into a sphere the size of a building. Or they ended as black holes, the endpoints of the very largest stellar deaths, where gravity won so completely that not even light can escape. The intermediate stars, stars like our sun, ended differently. When a star in this range exhausts the hydrogen in its core, it swells into a red giant, consuming its inner planets, shedding its outer layers in an expanding shell of glowing gas. What remains is the core, a white dwarf. Earth-sized solar mass, made mostly of carbon and oxygen, incredibly dense, and radiating heat into space with no source of new energy, just cooling slowly for billions upon billions of years. White dwarfs are already everywhere in the universe. They are among the most common stellar remnants we observe. The nearest one to our Sun, Sirius B, companion to the brightest star in our night sky, is roughly the size of Earth but contains the mass of our Sun. It is already cooling. It has been cooling for about 100 million years and will continue to cool for timescales that make that number look small. In the degenerate era, the universe is full of these objects, white dwarfs by the trillion, cooling toward what physicists call black dwarfs. The endpoint of a white dwarf's cooling, a cold, dark, inert object that no longer emits any detectable radiation. A dead crystal of carbon and oxygen the size of a planet, held together by quantum pressure alone, drifting through an expanding, increasingly empty universe. No black dwarf exists yet. The universe is not old enough. The oldest white dwarfs known, more than 11 billion years old, still have surface temperatures of around 3,000 Kelvin. They have been cooling for longer than the sun has existed, and they are still warm. The cooling timescale for a white dwarf to reach true darkness, to become a genuine black dwarf, is estimated to take on the order of 10 trillion years or more. Since the universe is only 13.8 billion years old, we have not yet seen a single one complete that journey. Every white dwarf currently in the universe is, in the context of its future cooling timeline, in the very early stages. And then there are the black holes. Black holes do not cool in the ordinary sense. They do not radiate heat like white dwarfs, but they are not, as was once assumed, completely inert. In 1974, Stephen Hawking showed theoretically that black holes emit radiation, now called Hawking radiation, due quantum effects near the event horizon. The process is extraordinarily slow for any black hole of astrophysical size. A black hole with roughly the mass of our sun would take approximately 2 times 10 years to fully evaporate through Hawking radiation. Hawking radiation has never been directly observed for astrophysical black holes. The predicted temperature for stellar mass and supermassive black holes is far below the cosmic microwave background, making detection impossible against background noise. It has been observed in analog laboratory systems, experiments that mimic the physics of an event horizon using other media, confirming the underlying mechanism. But for real black holes in space, the effect is too faint to measure by any technology we have or can envision. For supermassive black holes, the ones at the centers of galaxies millions or billions of times the mass of our sun, the evaporation timescale is almost incomprehensibly longer. It would take Sagittarius A*, the supermassive black hole at the center of our galaxy, approximately 10 years to evaporate through Hawking radiation. Supermassive black holes at the centers of galaxies would take closer to 10 superscript 1 years, a googol years, to disappear. These are numbers so large they have ceased to be numbers in any useful sense. They are more like categories, spans of time so vast that every process we have described in this film, the entire Stelliferous Era, the entire history of star formation, the 14 billion years since the Big Bang, fits into an interval shorter than a single heartbeat relative to them. But they are finite, and finite means they end. Now, there is a second possibility for the fate of matter, a hypothetical one, not yet confirmed, but worth understanding because it sits at the heart of how physicists think about the deep future. This is proton decay. The proton is a composite particle. It is made of quarks, held together by the strong nuclear force. In the standard model of particle physics, our current best description of fundamental particles and forces, the proton is, as far as we can tell, completely stable. There is no mechanism within the standard model for a proton to decay into lighter particles, but the standard model is almost certainly incomplete. Physicists have long expected it to be embedded in a larger framework, some kind of grand unified theory or GUT, that merges the strong nuclear force with the electromagnetic and weak forces at very high energies. And virtually every candidate for such a theory predicts that the proton is not truly stable. It can decay. The question is only how slowly. despite significant experimental effort. Proton decay has never been observed. The current experimental lower bound on the proton lifetime is 2.4 times 10 superscript 3 years, in a decayed channel into a positron and a neutral pion. The most recent results from Super Cameo Candy, a 50,000-ton tank of ultra-pure water buried a kilometer underground in a Japanese mine, surrounded by sensors watching for a flash of light that a proton decay event will produce, continue to push this number higher. A 2024 search using a 0.37 megaton-year exposure of Super Cameo Candy found no significant excess above background, setting the most stringent limits to date. Lower limits on the proton partial lifetime of 1.4 times 10 superscript 3 years in one decay channel, and 7.3 times 10 superscript 3 years in another. No event, no single confirmed proton decay in decades of searching. This does not mean proton decay is impossible. It means it is slow, slower than what current experiments can detect. The theoretical predictions from various grand unified theories span a wide range, and different frameworks give different timescales. If the proton eventually decays, and if the timescale for that decay falls somewhere in the range of 10 superscript 3 to 10 years, then in the degenerate era, the era of white dwarfs and neutron stars, proton decay would eventually become the dominant process eroding matter. Every white dwarf, every neutron star, every black dwarf, every atom of matter left in the universe would slowly dissolve, proton by proton, into radiation and lighter particles. If proton decay occurs on this timescale, a white dwarf fueled by the energy of proton decay would generate approximately 400 watts, enough to run a few light bulbs. An entire galaxy of such stars would have a total luminosity smaller than a single hydrogen-burning star today. But this is critical to say clearly. Proton decay is a hypothesis, not an established fact. It has never been observed. It may not occur on any timescale relevant to the future of the universe, or it may occur on timescales so long as to be practically indistinguishable from stability. Different physicists attach different probabilities to these scenarios. We do not know. If proton decay does not occur, white dwarfs will cool and crystallize into black dwarfs, and black dwarfs will slowly be converted to iron by pycnonuclear fusion, quantum tunneling nuclear reactions that proceed even at zero temperature, over timescales potentially exceeding 10 superscript 1 years. Without proton decay, matter is extraordinarily durable. What is not in dispute is the final state, regardless of path. After a sufficient span of time, all stellar remnants will have either decayed or evaporated or been consumed. What remains will be black holes, and then, eventually, not even those. The last black hole evaporates. The last burst of Hawking radiation disperses into space. And what remains is something that has a name, the Dark Era, but resists meaningful description. A universe of electrons, positrons, photons, and neutrinos. No atoms, no molecules, no chemistry, no structure on any scale that we would recognize as structure. An expanding, cooling, thinning void in which the average distance between any two particles grows without limit and the temperature of the universe approaches, but never quite reaches absolute zero. This is the terminus, not an explosion, not a collapse, just an asymptotic slide toward emptiness, across a duration that makes everything we call vast look like a preface. The fire that began with hydrogen collapsing under gravity, that burned in a trillion forms for a trillion years, that forged the atoms in your body, and the light in your eyes, and the warmth of every world that ever held anything alive. That fire goes out, not in a moment, not dramatically. It goes out the way all fires go out when the fuel is gone. Slowly, completely, without exception. There is a question that sits underneath everything we've described. A question that most people never think to ask because it requires holding two very different timescales in your mind at the same time. We know the universe is dying. We have established that. The star formation rate has been falling for 10 billion years. The last stars are dim red dwarfs burning their slow way through trillion-year lifespans. Eventually the fire goes out entirely. This is physics, not philosophy. It is what the equations say and what the observations confirm. But here's a question no one asks in the same breath. What if we are not just near the end of the universe's generative era, but near the very beginning of its biological one? What if life, anywhere in the cosmos, is only getting started? In 2016, a team of researchers, including Abraham Loeb of the Harvard-Smithsonian Center for Astrophysics, along with Rafael Batista and David Sloan of the University of Oxford, published a paper in the Journal of Cosmology and Astroparticle Physics. The paper asked a deceptively simple question: at what point in cosmic history is life most likely to emerge? Not most likely to exist right now, not most likely on Earth specifically, but across all of space and time, integrated over a full window during which stellar energy is available to drive chemistry. When is the peak probability? The answer they found was not reassuring in the conventional sense. Life as we know it first became possible about 30 million years after the Big Bang, when the first stars had created enough carbon, oxygen, and other heavy elements thought to be necessary for life. Life will end approximately 10 trillion years from now, when the last stars fade away and die. Within that window, the team calculated the relative likelihood of life emerging at any given moment. The dominant factor proved to be the lifetimes of stars. The higher a star's mass, the shorter its lifetime. Stars larger than about 3 times the sun's mass will expire before life has a chance to evolve. Conversely, the smallest stars weigh less than 10% as much as the sun. They will glow for 10 trillion years, giving life ample time to emerge on any planets they host. As a result, the probability of life grows over time. In fact, chances of life are 1,000 times higher in the distant future than now. 1,000 times. Sit with that number for a moment, not the metaphysical weight of it, just the arithmetic. If you were to distribute the probability of life emerging at random across the full window of cosmic history, weighted by how favorable conditions are at each moment, the peak is not now. It is not near our sun. It is not in the era of sun-like stars at all. The peak is in the far future, around dim red dwarf stars, in a universe that looks nothing like the one we inhabit. The smallest stars can live for up to 10 trillion years, giving life plenty of time to take root. So then you may ask, why are we living in the future next to a low-mass star? Loeb said, one possibility is we're premature. Premature. That word lands differently depending on how you sit with it. On one reading, it is disorienting. We have arrived too early to the party, before the main event, before the universe has reached its most biologically generative phase. On another reading, it is almost astonishing in what it implies about our place in the story. We are not the culmination of cosmic life. We may be the very beginning of it. Let's be precise, though, because precision matters here. The Loeb et al. Result is a theoretical calculation, not an observational measurement. It is based on assumptions that the probability of life arising per unit time around a star scales with a star's lifetime, that life requires roughly Earth-like conditions, that the formation of habitable planets around red dwarfs is not dramatically suppressed compared to sun-like stars. These assumptions are debated. The paper itself frames its conclusions carefully. It is computing relative likelihoods under a specific model, not asserting that life definitely will or will not arise anywhere. And the case of red dwarf habitability is genuinely, deeply unsettled. As of 2025, arguments concerning the habitability of red dwarf systems are unresolved, and the area remains an open question of study in the fields of climate modeling and the evolution of life on Earth. The challenges are real. Red dwarf stars, particularly in their youth, are not tranquil. They are magnetically active in ways that sun-like stars are not, and that activity produces flares, sudden releases of intense ultraviolet and X-ray radiation. M dwarfs have a high rate of strong flares, and potentially habitable planets are particularly susceptible to these phenomena due to their proximity to the host star, where the effects of stellar activity are more intense and the stellar wind is denser. Whether these flares can sterilize planetary surfaces, strip away atmospheres, or prevent the emergence of complex chemistry is an open question that researchers are actively working to answer. Then there is tidal locking. In order for red dwarf exoplanets to retain significant amounts of water in the habitable zone, they must orbit very close to the star and are likely tidally locked, meaning one side of the planet would eternally face the star and the other side would perpetually face away, creating great extremes of temperature. Whether life could arise and persist on such a world, whether thick atmospheres or global oceans or other mechanisms could redistribute heat sufficiently, is a question that climate modeling is only beginning to address. Astronomers still do not have definitive answers to some of the most important questions regarding these stars and the habitability of their planets. A 2025 Bayesian study concluded that the odds are approximately 1,600 to 1 against red dwarfs hosting advanced civilizations like Earth's, possibly due to the star's low stellar mass or limited time windows for the evolution of complex observers. Other researchers contest this framing entirely, arguing that the sample size, precisely one confirmed biosphere, our own, is too small to draw any meaningful statistical conclusions about what kind of stars can or cannot support life. This is where the science is honest. We do not know. We have one example of life in the universe. From one example. Inferring the distribution of life across all possible stellar environments is a fundamentally underdetermined problem. Every conclusion drawn is, at its base, an extrapolation from a sample of one. But the Loeb hypothesis, even as a hypothesis, even as one perspective in an ongoing debate, shifts something important about how we think about ourselves. Consider what it would mean if the calculation is roughly right. The universe has existed for 13.8 billion years. Life on Earth has existed for perhaps 3.8 billion years. Complex, multicellular life for perhaps 600 million years. Technological civilization for a few thousand, against a backdrop of 10 trillion years of potential biological time. The full window from first stars to last red dwarfs. Even the age of the universe itself is barely an opening act. If life is 1,000 times more likely in the distant future than whatever is happening now, on Earth, possibly elsewhere in our galaxy and beyond, represents a tiny early fraction of all the life that will ever exist. The overwhelming majority of potential observers in the history of the universe have not yet been born. They will emerge, if they emerge at all, in conditions we cannot directly observe from here, around stars that look nothing like our sun, in galaxies that will bear little resemblance to the Milky Way of today. We are in a very specific and non-metaphorical sense, the early ones. This inverts almost every intuition we bring to the question of our cosmic significance. We tend to assume that the universe has been building toward us, that its long history of star formation and planet formation and chemical evolution represents a preparation for the kind of complexity we see on Earth. But if the Loeb analysis is correct, then we are not the destination. We are a very early draft, and there is a second implication that is harder to shake. If life is so much more likely in the future, why are we here now? Why did life arise around a mid-sized yellow star 9 billion years into cosmic history, rather than around a red dwarf in the deep future? Loeb offers two possibilities, neither of which is more comforting than the other. One possibility is that we're premature. Another possibility is that the environment around a low-mass star is hazardous to life. That's the full binary. Either life on Earth arose unusually early. We are cosmically precocious, an exception to a future dominated by red dwarf biospheres we will never live to see, or the future will be biologically dark regardless of its physical resources, because the conditions around red dwarfs are simply incompatible with what life requires. The first answer is strange. The second is bleaker. There is a third possibility that neither paper explicitly considers but that hangs in the background of this entire discussion. That the question is simply unanswerable with what we know. We have no confirmed examples of life beyond Earth. We do not know whether life requires a sun-like star or can arise around a red dwarf. We do not know whether the emergence of life is common or vanishingly rare. We do not know whether the fact that we are here now reflects anything meaningful about the distribution of life and time, or whether we are simply one data point too isolated to tell us anything general. What we do know is this: the universe is more time ahead of it than behind it, vastly, incomprehensibly more. The Stelliferous Era in which we live is early. We are in the opening centuries of a story that will run for trillions of years. Whatever comes next, whatever life might or might not arise in the long dusk of red dwarf stars, we are not positioned to see it. We are the first witnesses to a universe still mostly unformed in its biological potential, looking out from an improbable early moment, asking questions that may not be answerable for eons, or perhaps never. And that is the most honest thing that can be said about where we stand. There will come a moment, not soon, not in any time scale that connects any human life or human civilization, or any species that will evolve from what we are, when the last photon is emitted in the universe, not the last photon ever produced. There will be photons for an almost unimaginable time. The fading infrared of cooling white dwarfs, the long trickle of Hawking radiation from black holes slowly evaporating across 10 years, or 10 superscript 1 years, depending on their mass, the last scattered remnants of the cosmic microwave background, itself already more than 13 billion years old, already stretched from its original 3000 Kelvin warmth to the 2.73 Kelvin whisper we detect today, stretched further and further by the ongoing expansion of space until its wavelengths exceed any meaningful measurement. The last photon from a star was emitted when the last red dwarf finally went dark. That happened in whatever future we are imagining, trillions of years ago relative to the moment we are trying to describe. The photon we're talking about now is something else. The final quantum of electromagnetic energy released by anything, anywhere, as matter completes its dissolution into radiation, and the universe finishes the slow process of reaching thermal equilibrium with itself. There is no instrument to detect this photon. There is no observer left to receive it. There is no difference it makes to anything, because there is nothing for it to make a difference to. It travels outward, as all photons do, at the speed of light. It redshifts as it goes, wavelengths stretching with the expansion of space, energy bleeding away into geometry of space-time itself. It travels through a universe that contains nothing that could interact with it, no atoms, no particles dense enough to scatter or absorb it. It travels alone. And at some point, it is too redshifted to meaningfully be called a photon anymore. Its wavelength has grown to match the scale of the observable universe, and then exceeded it, and the concept of a discrete particle of light has dissolved into something that physics describes mathematically, but that resists any image we might try to hold. The silence that follows is not empty in the sense of having nothing in it. There are still electrons. There are still positrons. There are still neutrinos, those ghost-like particles that barely interact with anything, streaming through what remains of space in all directions, cooling, dispersing, never finding anything to interact with. There are still photons of such low energy that calling them photons feels like a courtesy rather than a description. There is still space-time, still expanding, still geometry. But there is nothing that could call itself alive. Nothing that could form a structure. Nothing that could hold information in any configuration that persists. The universe is not dead in the way a fire is dead. Suddenly out, the heat dissipating quickly into surroundings. It is dead in the way a sound is dead after it has been traveling through an enormous empty room for long enough. Not stopped, exactly, just attenuated beyond the threshold of any possible detection, beyond the resolution of any possible physics. Not gone so much as indistinguishable from nothing. Let's step back from the very end and think about what the silence means, insofar as it means anything. The universe spent its first several 100,000 years opaque, so hot and dense that photons could not travel without immediately being absorbed and re-emitted. Then it cooled enough for atoms to form, and suddenly the universe became transparent, and light could travel for the first time. That light, the oldest light we can detect, is what we call the cosmic microwave background. We receive it today, 13.8 billion years after it was released, as a faint warmth of microwaves coming at us from every direction equally. It is the oldest message the universe has sent, a record of its state, when it was 380,000 years old. Every photon that has been emitted since is also a message of a kind. The light from the first stars, light that has been traveling for almost a full age of the universe, shifted so far into the infrared and radio that instruments like the James Webb Space Telescope can only barely reach it. The light from distant galaxies, carrying information about star formation rates and gas composition and the distribution of dark matter in the early cosmos. The X-rays from neutron stars, the gravitational waves from emerging black holes, the faint radio whispers of pulsars rotating dozens of times per second. All of it, messages. The universe talking to itself through the medium of physics, across the medium of time. At the end, that conversation stops. Not because there is nothing left, not because the laws of physics cease to operate, but because there is nothing left for any information to be encoded in, and nowhere for it to go, and no process capable of reading it even if it existed. The conversation ends not in an argument, not in a climax, not in anything that would register as an event if you were somehow present to observe it. It ends in the way conversations end when everyone has fallen asleep and the room has grown dark and there is no one left to speak. There is one more thing that deserves to be said plainly, because it sits at the edge of everything we have discussed, and it is easy to slide past it on the way to something more comfortable. We do not know with certainty that any of this is correct. The framework of the 5 ages, stelliferous, degenerate, black hole, dark, is built on our best current physics. It assumes that dark energy continues to act as it does today, that proton decay either does or does not occur on timescales within a certain range, that Hawking radiation is real and black holes do eventually evaporate, that the laws of physics we have discovered apply across all of time and space. These are reasonable assumptions. The physics behind them is robust, but we are extrapolating across timescales that no experiment has tested and no observation has reached. The universe may behave in ways we have not predicted. There may be processes at work at extreme timescales, quantum gravity effects, phase transitions in the vacuum of space, structures that emerge from complexity in ways we cannot anticipate, that alter this picture. We cannot know from where we stand. What we can say is, this is what the equations give us, applied consistently with our best current understanding. And equations give us darkness. They give us white dwarfs cooling into black dwarfs, black holes evaporating into thermal noise, protons possibly decaying or possibly not, across spans of time that exceed 10 superscript 3 years. And then after all of that, a universe that expands forever toward temperatures indistinguishable from absolute zero, a universe in which the distance between any 2 particles grows without limit, a universe that will never again produce a star or a planet or a molecule or anything we would recognize as organized matter. The last star has already been born. Somewhere in the universe right now, probably in a small, quiet galaxy, probably a red dwarf too dim to see from here, is a star that will be the last. It doesn't know it. The gas cloud that formed it didn't know it. It is burning the same way every other star burns, through the same physics, on the same time scale, entirely indifferent to its own finality. It will burn for trillions of years. It will outlive everything we know, and then it will go dark, and the universe will continue, vast, cold, expanding, empty of fire, for a duration so much longer than the Stelliferous Era that the era of stars will seem, in retrospect, like a brief flicker. A match struck in an enormous dark room, burning for a while, then out. The room remains. Dark, enormous, quiet. That is where we're going. Not tomorrow, not in any time scale that connects to any experience any living thing has ever had or will have, but going nonetheless on a trajectory that is clear, at a pace that is measured toward a destination that is certain. There is no comfort here, no redemption arc, no cosmic purpose that gets revealed at the end. Just physics, just time. Just a slow, indifferent unwinding of everything that was briefly wound up. You're made of atoms forged in stars are already dead. You are alive in an era that will look, from the far future, like the first seconds of a very long night. You are conscious of all this, briefly, which is more than the universe itself can claim. The silence is coming. It has been coming since the beginning. And one day, in a time so distant it cannot be named, in a universe that will bear no resemblance to this one, it will arrive.